What is it that makes birds unique? Have you ever wondered how birds can fly? And why can't I? It looks so effortless. But is it? Let's learn more as Lyn Rodger, bird enthusiast, West Pasco Audubon member, and Honeymoon Island State Park volunteer interpreter presents a program on the superb efficiency found among and under all those beautiful feathers. So, a little bit about Lyn Rodger. Lyn started actively birding in 2005 when she and her husband moved to New Hampshire, where they overlooked a meadow to the Great Bay Estuary. After a 2-semester course at the University of New Hampshire Extension Division Marine Docent Program, Lyn led school groups at Great Bay Discovery Center, took nature programs into schools, and led interpretive walks on the Isles of Shoals, a rocky island 9 miles off the coast. She has also completed the Florida Master Naturalist Coastal Program. Currently, Lyn leads interpretive walks on the Osprey Trail at Honeymoon Island State Park. As part of her walk, she talks about and compares their nesting raptors, osprey, great horned owl, and bald eagles. Thank you, and join me in welcoming Lyn Rodger.
Thanks for that nice introduction, Christine. Hello, everyone. We're meeting via Zoom this season since we're unable to meet all together. As much as I'd like to be with you in person for our indoor meetings, I'm rather enjoying this new challenge. My presentation was inspired by one given during the University of New Hampshire Marine Docent course. While an active member of the docents, my interest in birds increased as I led walks through part of a blackback and herring gull rookery on Appledore Island and the Isles of Shoals. For those of you who haven't recognized my virtual background, I'll share a beautiful birding spot at the end of this presentation. So, let's zoom. What makes birds unique? How can birds fly, and why can't I? Today it'll be a basic overview of bird physiology. Each of the topics covered could be expanded with many more tidbits of information. There are about 10,000 species of birds in the world, the largest of which is the ostrich. Can be anywhere from 225 pounds to 350 pounds and 7 to 9 feet tall. Look at the room you're in. Most houses have ceilings that are in the range of 8 feet. So this bird, if he were standing next to you, would be pretty imposing as he ducked his head to avoid the ceiling. Notice that his wings are pretty small. A bird that size really can't fly. He would need enormous wings, which would mean he'd need even more wing muscles, chest muscles, to be able to fly. But he's a good runner. The smallest bird in the world is the bee hummingbird, which weighs less than a dime. It could sit on the tip of a finger. To start, I'd like you to meet my mother-in-law. She often said she wanted to come back as a seagull, both because they looked as though they were having such fun up there in the sky, and because they hoped to clean up the environment of all the food stuff and stuff that humans leave around. In a way, she has come back, because whenever I see gulls enjoying themselves in the sky, I think of my amazing mother-in-law. We all enjoy birds around us, but rarely do we think about how they can do what they can do. Many migrate thousands of miles twice a year. Imagine if we tried to do that under our own power. So, what makes birds so unique that they can do that and more? How is it possible for them to defy gravity and make flying look so effortless? What makes a bird a bird? Feathers. Only birds have feathers. No other animals have them. So let's look at feathers. This is the right primary flight feather of a herring gull. Notice that one vein is much narrower than the other. That's the leading edge of a flight feather. and it's less flexible so that it prevents midair twisting. Now let's take a look at the parts of a feather. The calamus or quill is at the bottom. The full-grown feather is, the calamus is hollow. When the feather first starts coming out of the skin, there are blood vessels in there that help the feather to grow. The rachis is solid but very lightweight. And the veins are made up of barbs that the bird will zip together like hooks in a zipper. And take a little close-up of that with the barbs and barbules. Feathers are a bird's home. Each feather, except for the phyloplumes, is controlled by muscles in the skin. Contour feathers. They're overlapping like shingles on our house. They provide the siding for the bird's home. Flight, body, and tail feathers give aerodynamic shape and the ability to fly. Down feathers are the inner layer next to their skin, providing both insulation for warmth and cold. Semiplumes are another layer of added insulation intermediate between the contour and the down feathers. And there's a photograph of an actual semiplume feather. Now the phyloplumes are different. They are pressure and vibration receptors. So you have apps on your computer or your smartphones that tell you all kinds of information. Phyloplumes are the bird's app, and it lets them know when other feathers are out of place so that they can preen them and get them back where they should be. Birds also have bristle feathers, usually around the mouths and eyes and nose, and they offer protection from debris that's around, like our eyelashes do, and they possibly help to channel food into a bird's mouth. Wing feathers. The primary feathers provide thrust and control. The secondaries provide lift. The tertials fill the space between the secondaries and the body. And coverts cover where all the feathers connect to the bone so that it looks wonderful. Some birds have beautiful display feathers. Can you imagine having a hat made of this bird's feathers? Or maybe the whole bird sitting on top of your head? Or a feather boa around your neck? In the late 1800s, early 1900s, these birds with beautiful displays almost went extinct. In 1918, the Migratory Bird Treaty was made with Canada so that these birds were no longer allowed to be hunted for their plumage, and it's still in effect today. All birds have a uropedal or preen gland that supplies a waxy substance that the bird then spreads around on its feathers. Sometimes you'll see it pick some stuff out of that uropedal gland and put it on its feet and then put it on the top of its head. It provides moisturizer, conditioner, and bug repellent. They preen to make their home watertight and airtight, but mostly to make those feathers last longer because they are super dependent on their feathers being in good shape. This female American redstart shows feathers that are in beautiful shape. It was at a banding station, and I had the opportunity to release her. It was put in my hand, and I could feel the heartbeat. I could feel the prickle of its toes, but there was no weight at all. It was like holding air. And when I opened my hand to release her, she sat there for several seconds and then took off, and it was like releasing a puff of energy. If you're ever at a banding station and they say, "Who wants to release this bird?" raise your hand and do it. It's really quite a wonderful experience. Birds molt gradually, usually after the breeding season and before migrating. This red-shouldered hawk is replacing some of its tail feathers, as you can see, and it's slightly out of focus because it flew from one side of my fence to the other, and that was the best one I could get. But you can also see the primary feathers, kind of fingers all spread out there as it's losing wind and spreading everything out so that it can land on the other side of the fence. Anhingas dry their feathers, cormorants do, and her back is to the sun, as you can see the shadow on the rocks. If it's a cool day, she might be drying her feathers and getting warmth from the sun. If the breeze is from the front, might be cooling off in the breeze. And notice those tail feathers. I was surprised when we found a feather at how stiff they are. The white striping on this tail feather isn't white at all. It's the corrugation. It's like corrugated cardboard. And it's almost as stiff as corrugated cardboard. There's another little feather here that we don't often see. This little, it's called an alula, and it is in relation to a person's thumb, which is covered by 3 to 5 feathers, depending on the species. Normally it lays flat and you don't notice it, but they'll raise their alulas to prevent stall during very slow flight. Wood stork, the feathers provide good insulation, and the white feathers reflect the heat of the sun. Now this guy was just after a storm with high winds and torrential downpours. This is at the Embassy Road rookery, between the rookery and Embassy Road itself. There was a little pond there, and he just looked so bedraggled. The wood stork stands about 3 feet tall. His wingspan is 5 feet, and he weighs around 5 pounds. But look at the size of his body in relation to the whole bird. You can see the curvature of the wing. The curvature, like the curvature on airplanes now, makes it so that the wind is traveling faster over the top of the wing and therefore provides lift. And some birds can control the amount of curvature there is there and how much lift there is. Notice this kind of pinkish area here. The feathers are thin, and that's the light shining through somewhat translucently. The other thing about bird legs is they bend in the wrong direction. This looks like it should be a knee, and yet it's really an ankle. Their knees are up here under the body itself. Wing shape and purpose. Going down the left-hand side, the first wing is for active soaring. It's long and narrow for a bird to fly without flapping, and it's dependent on wind currents. You have gulls, albatrosses, gannets, and the magnificent frigate bird that we occasionally see out at Honeymoon Island. Second wing is passive soaring. Long primary feathers that spread out, creating slots that allow the bird to catch the thermals. Eagles, most hawks, storks, vultures. The bottom one is elliptical, good for short bursts of high speed. Crows, ravens, thrushes, sparrows, owls. On the second column, the top is for high speed. It's long and thin, fast, can maintain speed for quite a while. You have your ducks, falcons, terns, sandpipers, and osprey. And the bottom one is much too large and compared to the others. It's for hovering and would be a hummingbird wing. Kestrels can wind hover and often do when they're hunting their prey. The colors on this, the red are the primary feathers, orange are secondary feathers, yellow the primary coverts, green secondary coverts. The aqua is that alula that I mentioned before, and blue are marginal coverts, and the purple are scapulars over the shoulder. This is from the Cornell Lab of Ornithology Wing Types handout. So let's take a look at the skeleton. Birds have a unique anatomy for strength and power. They have fewer bones than we do. Wings and legs have the same basic parts as our own limbs, but they're highly modified. We have 29 bones in our forelimb. The bird has only 11. Has bills and beaks instead of teeth and heavy jaws. again saving weight. Has hollow bones with internal support struts. And I had to see for myself. This was a chicken thigh bone that I had put in a stew pot and then was able to break apart afterwards so that I could see that structure that's in there. The biggest muscles on a bird are flight muscles. The keel holds the end of the flight muscles, and think about your Thanksgiving turkey or a whole chicken that you're cutting apart. And if you're cutting off the breast meat, you're cutting it off of the keel. The larger the keel, the more wing muscles there are. The pectoral muscles are the major muscles that move the wings and pull the wings downward. Very little muscle is found in the wing itself because that would add weight and make the wing have to be larger and more difficult to move. The supracoracoideus, the minor pectoral muscles, are the ones that pull the wings back up. And they're attached to the wings by large tendons that reach up and over the shoulder and out the wing to pull it back up. And if you bought chicken tenders, that tendon that's in there is the tendon that helps to pull the wing back up. The wishbone helps to hold the skin and the feathers away from the muscles so that they don't get in the way. In a man's chest, the chest muscles equal about 1% of his body weight, whereas in birds, it's 15 to 30% of the body weight. In the circulatory system, the bird heart and the human heart are both four-chambered. In the bird, the valves are a little bit smaller. The walls are smoother for less friction. The resting heart rate is much higher, and the size of the heart in proportion to the body is larger than ours. Resting heart rates of birds: in a mallard, 155 beats, crow, 345, house sparrow, 460, and hummingbird, 615 beats per minute. You know, I mentioned feeling the heartbeat of that American redstart that I released, and it was just beating like crazy. Just fun and exciting to feel. A bird's respiratory system is the most efficient of all vertebrates. Flight is an energy hog, so it demands an efficient way to take in oxygen and exhale carbon dioxide. Birds do not have a diaphragm. Their lungs are fairly rigid and small, so they rely on compression and expansion of the rib cage, as well as 7 to 9 air sacs in the body cavity, depending on species, as well as some hollow bones to breathe efficiently. Humans' lungs are bidirectional. Oxygen is mixed with CO2 as breathing moves in and out. Take a deep breath for a moment and just feel your body. As you breathe in, your lungs are expanding. Carbon dioxide mixes with the oxygen. As you exhale the carbon dioxide, some oxygen is exhaled as well. Birds' breathing, on the other hand, is unidirectional, which means there's always a supply of oxygen-rich air in the lungs. How does this work, you ask? A bird's lungs are a labyrinth of a variety of interconnecting bronchial tubes. Most of the inhaled oxygenated air bypasses the lungs and goes into the posterior air sacs. The oxygen-rich air already in the posterior sacs is pushed into the lungs, where the oxygen and carbon dioxide exchange takes place. The oxygen-depleted air is pushed from the lungs to the anterior air sacs and exhaled from there. A complete cycle takes 2 full breaths. So, while there is some mixing, there is a constant stream of oxygenated air in the lungs. Digestive system. Our kitchens have pantries in them. Birds have a crop. They can store food in the crop to eat later or to carry to their babies. Owls don't have a crop, however. They eat their animals whole and digest it in their two stomachs. The proventriculus is the first stomach where the liver starts providing digestive enzymes. One other thing, do birds have milk? Pigeons and flamingos actually make crop milk to feed their young. Pigeons will feed theirs for a couple of weeks, but flamingos will feed crop milk to their young for a couple of months until the filter feeding apparatus is developed enough for the young to get their own food out of the water. From the proventriculus, food goes into the gizzard where it's ground up. Hopefully the digestive enzymes that have started in the proventriculus have softened the bones and stuff so that they are digestible. We eat food, we digest it in 6 to 7 hours, and it takes 1 to 3 days for us to excrete it out the other end. Birds, on the other hand, can digest their food in 45 minutes to a couple of hours. The owl might take 4 to 6 hours to digest a whole animal, and if it's really big, maybe it might come out the next day. And they have to eject the pellet. They wrap up all the fur and the bones and eject it out before they can eat again. Then the food goes down through the intestines. Kidneys take the moisture out. There's no bladder, and everything comes out the cloaca. And that's what I found on my windshield one day. The white parts are the uric acid, and the darker parts are the poop. This is what came out of an owl pellet, fur, and a couple of views of the head bone. Birds store energy in their fat. Because they digest so quickly and excrete so quickly, they have to be eating all the time. This bird bander is blowing on the feathers of the bird's belly so that he can see the fat supply, which is the energy supply of a migrating bird. Birds have a very efficient release of their stored energy. Reproduction gets efficient again. The male's testes only enlarge when breeding, and they shrink several hundred times after breeding. So what triggers hormones to enlarge the ovaries and testes? I was at a Rhodes Scholar evening program in Sarasota several years ago, and a couple who volunteered to be ground crew for the flight south of whooping cranes gave an interesting talk. Whooping cranes at that time, quite a few years ago, had only one flock left. And biologists worried that if disease, bad weather, or human activity decimated the flock, they would become extinct. So they took some of the eggs from that flock to raise in Wisconsin. They were fed by costumed people so that they wouldn't lose their fear of people. I mean, these people were draped in white. They had their hand was all covered in white with a red top on the top of its head to feed them. They also taught them to follow an ultralight so that they could lead them down to Florida where they wanted to have them winter. Took them back to their breeding grounds, and they wouldn't breed. They really wanted to get this flock going, but they wouldn't breed. But they had observed the courtship behavior of sandhill cranes, and I had quite a time watching these sandhill cranes that you see dancing and displaying before each other, and didn't think an awful lot about it other than that it was fun and it's their mating season. But what it is, it's activating the hormones. It's activating the gonads to grow larger so that they are ready to mate. Other triggers that birds have are day length, temperatures, migration, the rituals, singing, dancing, bringing food or bringing nest materials. So when I see birds acting differently than they do most of the year, that's a time to watch them a little more and see what they're doing, because their behaviors are doing something. And here we have reproduction, the cloacal kiss. They have that one opening, the cloaca, and the birds twist so that he can add sperm to her, and it takes place over a couple of seconds. Females have one functional ovary. Fertilization happens in the upper oviduct. Albumin and shell are added as it comes down the oviduct. Birds are oviparous. They don't carry the developing embryo the way we do. They got to save weight so they can fly. My daughter has chickens, and I went out to her chicken coop one day to gather eggs, and there was one egg there, and I picked it up, and it was still warm. And it felt like one of those squishy pink balls that kids play with. And I took it in and I said, Chris, is there something wrong with this egg? And she says, no, they have to be soft to come out of that oviduct, that cloaca. And when it hits the air and cools off, then it hardens and becomes the eggs that we see. You know, they don't always just come out of the refrigerating section in the supermarket. A bird's body temperature is 104 to 105, 110 degrees. Fast heartbeat, high metabolism. To stay warm on a cold day, they can bring one foot in, tuck their head in under their feathers, fluff up the down that's underneath, and keep the outer feathers, the contour feathers, tight to stay warm. Their feet have a heat exchanger. You notice there usually aren't feathers on their feet. They have scales, less likely to have frostbite in cold weather. The heat exchanger is in this center area. The arterial blood will go down, whereas the cold blood, the venous blood, will go back up. They can also close off any of this open work area here to shunt the heat, or to keep their feet from getting extra cold. And if they want to cool off on a hot day, they can swim. They also bathe to keep their feathers clean. They have no sweat glands, so they can enjoy a bath, pant like a dog. The gular fluttering draws cooling air into the air sacs. It also releases moisture, so birds need to have water around and can dehydrate fairly easily. He's also got his wings open so that he can enjoy a nice breeze, and that might help to get rid of parasites as well. And then one day at Honeymoon Island, there was no breeze on the ground. It was a super hot day, and I saw this little kestrel up on a snag. He's not puffed up to stay warm. He's got all his feathers opened, like opening all the windows on your house so that he can catch the tiniest little breeze up there to cool off on a hot day. And birds also seek shade. You'll find them fluttering around in the bushes on a hot day. Ospreys, we're talking about voice. Ospreys have a familiar call. They have a mockingbird. Did you recognize Carolina wren, flicker, jay, wood thrush, phoebe, and tufted titmouse? I hope so. The voice box is not located in the larynx like on mammals. Instead, they have a syrinx, which is located where the bronchi from the lungs meet up the bottom of the trachea. To vocalize, a bird modifies the tension of those muscles around the trachea, the syringeal muscles, and modifies those to squeeze the air that's in the center, causing the tympanic membranes that are inside the syrinx to vibrate. The bird has great control over these muscles and is able to produce a variety of sounds, and some of them at the same time. We utilize only about 2% of the air passing our vocal cords. The syrinx uses nearly 100% of the air passing through it. So we get complex sounds like those of a loon. I'm often asked about the sounds that owls make. We have the great horned owl on the left, and the barred owl on the right. I love those sounds. I hear them in the middle of the night. I've never been able to find the one out behind our house, never been able to see it, but I have seen them elsewhere, especially at Circle B Bar. Hearing. Most birds have their ear holes covered with tiny feathers, which is specially designed to cut down the noise and permit sound waves to pass through. They're like the foam covers that you see on microphones. And it helps to keep them streamlined for flight. This roseate spoonbill doesn't have his all covered up with feathers. The owl disc feathers are somewhat stiff, and the facial muscles allow them to be positioned for the best reception. Note that the arrows are pointing to where the ears would be behind those facial discs, and they're at different heights and slightly different sizes, which helps the owl to zero in on the mouse or whatever its prey is on a dark night. The flight feathers on the owl, the leading edge of the comb, it's shaped to, it's like velvet and shaped to alter the air currents to stop the sound. So they totally silent when they fly. Vision is most highly developed of any animal in birds. Those who are preyed upon have the eyes on the side of the head, like this American robin. Monocular vision, they see out of the eye, either side of their head separately, don't have any depth of field, but they do have almost 360-degree view so that they can see whether there's a hawk out there or something else that is stalking them. Predators, like this red-shouldered hawk, have their eyes on the front of the head, which gives them depth of field and binocular vision. And their eyes are pretty stationary. Gulls can move their eyes somewhat, hawks don't. You've heard of the eagle eye. Eagles have the most highest eyesight of any of the birds. They soar on thermals. They often wait for the day to warm up before hunting their food. Soaring saves energy, but finding food from high in the sky requires good eyesight. They have color and UV vision. Some of the cones that are in their eyes also have droplets of oil in them, which helps to sharpen the vision even more. Hawks have most birds have two foci or focal points, especially in the hawks. They have a flatter retina that allows them a much wider in-focus vision. Eagle eyes are almost as large as ours, as human eyes, but the sharpness is much greater than that. It means that eagle flying 1,000 feet up has a radius of about 3 miles that it can see and find its mouse or rabbit. And if you've seen eagle nests that have been blocked off in high traffic areas, they're blocked off for about a football field. So if you're sitting in the stands at one end of the field and an eagle is sitting on the goalposts at the other end, he could technically be able to read your program in your hands. Pretty amazing. The eyes have it. The owl eyes, on the other hand, are fixed. The polymer composite of the actual size of the skulls are on the bottom there, showing the relative difference between osprey, great horned owl, and bald eagle. The owl eyes, you'll notice, have a protrusion here. Their eyes, instead of being totally round, are a little bit more cylindrical. And because they're nocturnal, they don't have all of the color seeing cones that other birds have, but they have millions more rods that detect movement and sight in the dark. So if we're in a dark room and somebody turns the light on, it takes several seconds for us to be able to see. The owl eyes adjust instantaneously. In a room that we think is dark, if there's a little bit of a smidgen of light, the owl is able to see pretty well there. If it's sitting on a tree branch and has sun on one eye and not on the other eye, they adjust separately. If the great horned owl's head was the size of ours, the eyes would be about the size of grapefruit. And notice on the eagle, and the others here too, there's a little bit of a bony protection in the front that protects against branches as they're coming in. That protects against babies moving around in the nest when they're trying to feed them. Birds have different shaped bills or beaks, whatever you want to call them. The short, pointed beaks are for ripping flesh. Swallow and other insect-eating birds have short, wide beaks for capturing insects. The cardinal has a stubby, powerful beak to open seeds, and different seed-eating birds have different size, powerful beaks, depending on the size of the seeds that they like to eat. Short, slender forages for insects under leaves and in bark. Long, chisel-like is looking for bugs in trees. And long and slender reaches for nectar. Then we have the pelicans with the great big pouch for scooping up fish. And the cormorants, hooked for snagging their fish. Long and straight for catching and spearing. And if you can see on your screen there, notice where the tongue is. It's attached to that bottom mandible so that the bird can expand everything and get that huge fish or whatever prey it's trying to eat down its throat. Long and narrow probes into the soil, and if you see a lot of the shorebirds have different length beaks, it's for poking into the mud and the sand to different levels for different prey so that they're not all going for the same thing. And then you have the long rounded one for foraging underwater. The roseate spoonbill has a super sensitive bill there. It can't see what it's eating, but it can feel it and sense whether it's prey or mud or leaves and snaps shut very quickly. Woodpecker skull. It's like, well, our bicycle helmets are trying to mimic the woodpecker skull, but his brain is very tight in his head, unlike ours, which are a little bit looser in a bicycle helmet. The beak is in 3 parts. The keratin is the outer layer. There's a foam middle layer and a dense bone inside layer that spreads the energy throughout the body. But look at this little downy who's really pecking away. The woodpecker's tongue on the left one there is retracted. On the right one, it's extended. Once he's poked a hole into the tree, he's got an exceptionally long tongue that wraps around his skull and is anchored at the base of the bill. Their feet are also pretty amazing. We have perching birds that sit on a branch, and when their weight is down on their feet, they cannot come off the branch. It just makes them clasp tighter. You have climbing like this red-bellied woodpecker. And the osprey has a helix that's movable and allows the osprey to turn the fish aerodynamically head first. The osprey and the owls have that movable helix. We got feet for swimming, and the snowy egret has feet that spread out over the mud or grasses that it's wading on so that it won't sink in. This is the talons of an actual osprey that were preserved. Notice the scaliness on the left one and how sharp those talons are. He's got a good grip. The one on the right is showing the underside of the talon, and you can see all the spicules that help it hold on to the slippery fish. And here he is, having turned the fish forward so that it's aerodynamic. Every now and then you'll see it, well, they've only caught it by one hook of a talon, or you'll see the fish with its mouth wide open, acting like a sea anchor or an air anchor, but they're pretty good at catching their fish. Shearwaters and albatross spend most of their time over water and locate their food using smell. Turkey vultures have the most advanced smell of all. They like their carrion slightly rotten. 4 days is ideal. Black vultures don't have as good smell as the turkey vultures do. And they'll watch the turkey vultures up in the sky to see when they're starting down, and they'll come in to get in on the prize that's down there. And the black vultures dominate. They will kick the turkey vultures out of the prey and finish it themselves if they can. Many birds have a sense of smell. They can breathe through their nose, filtering out dust and other particles. So, what enables a bird to fly? They're very light in weight, thin hollow bones, very light, strong feathers, no teeth or jaw bones, oviparous, no bladder, male testes shrinks when they're not breeding, and female has only one functioning ovary. They have a very fast metabolism, high body temperatures, feathers insulate against heat and cold, very efficient oxygen consumption, fast digestion, a large 4-chambered heart. This is basic physiology. Each category can be developed with lots more interesting information. Keep searching for answers. And as you're looking at the birds out there, think a little bit about how they're doing what they're doing. And now for a tip on one of my special birding spots. My virtual background shows some ring-necked ducks enjoying the winter here on Grassy Lake. Shortly, they'll migrate back to their breeding grounds in Canada and the northern US. The photograph was taken from the beautiful new bird blind at J.B. Starkey Wilderness Park in Newport Richey, Florida. This bird blind was a project of West Pasco Audubon with major funding by the Duke Energy Foundation. Thank you to all who made this possible. Check out the events on westpascoaudubon.com or your nearest Audubon chapter for bird walks near you. I hope to see you out there.